Right. Um, Back when we were talking about the n-body problem, I mentioned that Unity wasn't threaded, but let me get a share screen going here. Unity is built on C#, which gives us access to threaded programming. Here's a link to some interesting stuff. Threading is a lightweight version of parallel programming that takes advantage of multi-core architectures. In this way, if you have like a computationally intensive task, you can run it in the background on a separate thread. And the idea is that the gameplay doesn't have a lag hiccup as it's waiting for this heavy task to be accomplished. The drawback with Unity is that you can't really do multi-threading, at least not with the traditional C# threads inside the Unity API operations. You can only use Unity API operations in the main thread. And this involves a lot of get operations and set operations and constructors. So I'm actually not going to go through this in detail here because Unity has instituted something called the job system, which is Unity's version of threading, and it's much, much better than what we have to do in order to kind of kludge around Unity's API limitations. It's designed for Unity. It has the tools for actually moving things in and out of threads. It has a lot of safety checks and so forth. So I'm actually not going to go through these examples here, but there's a couple of them there, some from Bunny 83 referenced here, showing how to set up threads, use locks, make things sleep, have a callback function that gets invoked when the thread has completed, and so forth. It has like wait for functions that spin waiting for something to finish, and ability to run threads. So, and the examples that I give you are mostly busy work kind of examples. There are a couple of files that you'll see, and you can have a look at them if you want to, but I highly recommend the Unity job system as a way to do threaded programming in Unity. So I'm gonna, and I will show you that I actually did get speed up. This is a runtime for 2 busy work programs, one sequential and one threaded, and the speed up that you get, which levels out at 8 CPUs, which is how many 8 threads, which is how many CPUs my computer had at that time. So I'll let you read through this yourself and the issues that go into parallel programming if you're unfamiliar with them, things like locks and atomic operations and putting threads to sleep and making them join each other and assigning names to them. And there are a couple of different folders that I'll provide you with that show this old, basically Unity 2017 version of threading. Let me switch here to something else that uses threading. And this goes back to Sebastian Lemieux's procedurally generated terrain. And he wanted an endless terrain, one that goes infinitely off into the distance. And the way to do this is to procedurally generate terrain as our character or whatever moves across the landscape. And so the idea here, I'll leave the scene view running and I'll do a Shift F so that it tracks my viewer that is designed to automatically run across this landscape. And you'll see exactly what I mean here by an endless terrain that's using the basic tool that Sebastian Legueux built up to his lesson 5. But he's extended it now so that it's building terrain out into the out in front of my character here as he moves along. So the thing you can see here as he's going along is that he's building terrain out in front, and the terrain behind him is disappearing. It's actually being put to sleep, so it's not computing. But even in this form, threaded, we are seeing some hiccups here, some performance hiccups as this thing generates the terrain in front of it. And he did a whole bunch of fancy stuff with level of detail and matching up the scenes and doing all this other stuff. It's all in his website for you to have a look at if you're interested in it. The problem being the threading uses this callback feature to see if something, to offload the job onto a separate thread, keep track of whether it's completed or not, and only apply it, only apply the texturing and coloring and creation of the texture when that thread has completed. You remember we had the height map and the color map that we generated. He's added this level of detail that's keeping track of how close we are to the chunk of terrain that we're interested in. But he has these system actions that are the callbacks, the delegates that the system calls when it's done creating one of these meshes. The two methods we use are the request mesh. So this is asking for it to create a thread that's going to generate the mesh data using that map generator that we saw before. And we have the on mesh received that catches this return data once it's been processed by the separate thread. And at this point, we'll create the mesh and do the update callback. So we're starting a thread as a delegate mesh data thread. So here's all this threading stuff that we're doing where we're creating a thread. And it's passing to it slots for the map data, the level of detail, and the callback that it's going to use when it finishes, when on mesh data received comes back from that request of mesh data. And here it's starting the thread. So this is loading stuff into the thread. This is loading stuff into the thread, and then this is starting that thread. The thread generates the mesh, does the generate terrain mesh, we have to be careful to lock this to ensure atomic operations. We add the callback that is going to go into a queue that we maintain of things that we're watching to finish. The map thread info is a struct that accepts various data types. It'll accept both mesh data and later map data. So now this callback is in that queue that we're going to watch to see when one of these things finishes. Incidentally, the queue is declared like this. So the whole reason we do this is so that we can take the results from the thread and apply them to the actual object. So in our update function, we're watching this queue. And if the count ever goes above 0, that means something has finished, and we can then unpack that object that's in the queue, uh, 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 execute its callback, whatever it is, with the appropriate parameters, and then update those visible chunks that we need to keep track of. We also want to keep track of chunks that we've already made. If our character ever turned around and went back and there was a chunk that had already been made, we'd like to have it available to us. And we do this by using a dictionary where we keep track of the names of the chunk according to their coordinate X and Y offsets. And so we can, if a chunk has already been made, then it's in the dictionary and we don't have to put it there. Otherwise, we can just pull it out of the dictionary and use it. If it doesn't exist, of course, then we make one, and we have to make a new terrain chunk with all of its appropriate stuff. The terrain chunk class is fairly complex since it handles the creation of the mesh object as well as its updating and its materials and colors and all that other stuff, built pretty much on top of what we looked at back when we did just a simple procedural mesh. Here's the map data queue, and here's the update to keep track of that, and the mesh data queue, which does exactly the same thing. So we're queuing and dequeuing things as things appear in the in that queue of finished tasks. After all that work, here's a comparison of the endless terrain with and without threading. And the threaded one is the solid line. It's always above with an average here of about 50 some frames per second, whereas the unthreaded one is down around 35 on average. This is how many frames get done in a certain amount of time by the threaded version versus the unthreaded version. As you can imagine, a lot of the overhead of this is the rendering, not the computing. But, and there's a lot of noise in this. It's not terribly satisfactory. But it is what you could do with threading back in those days, in the 2017 era. Let me just show you this now with an actual airplane flying across the scenery. And let me maximize it. And whoops, sorry, it'll recover. So you notice I've added fog. This lets us not see the terrains that are being added up ahead. I've got these beacons that my goal is to go through the tops of the beacons. But of course, to make life interesting, the beacons fire missiles out at the homing missiles, which is one of the exercises that we'll do. And so we score points by going through the beacons, and we lose points by getting shot down by the missiles, which, where are some missiles? Oops. Well, I'll let you play with that at your leisure. I will put a copy of this out there. All right, so I'm going to stop sharing, and I'm going to end the recording, and I'll come back in and talk about the job system, which is the real parallel programming, the real threading system for Unity. So I'll stop recording. Bye. See you in class.